Okay, let's start. Let's begin. Hope you're all doing well, etc., etc. Last 3 weeks of the course, as we already talked about it before, we discussed what can be called multi, whatever, variable calculus. Now, in general, what we're trying to do is to generalize whatever we said about function of single variable to functions of more than one variable. On the other hand, we have 6 lectures for this, and we talked about what single variable functions for something like 35 lectures. No.
If you take into account the first.
Yes, in ones well. Something like Labrut, 32, something like that, 31, more than 30 lectures. So what we're going to basically do is, first of all, we'll discuss the things from the most technical point of view possible, without any proofs, without any I don't know what, just see this is the problem, how do we solve it? Yet here in the lecture, I can give you some intuition, maybe, when it comes to 2 variables. We can still imagine it because 3-dimensional graph, I'll talk about it shortly. And the second thing, I think, is that we're not going to go through everything we did in single variable calculus. What we're basically going to do is the following things. First of all, this will be a schedule. Let's write it down, schedule. Something's missing, probably. Yeah, whatever. You can correct me if you want. Huh? Yeah. Schedule is good enough. How do you write it? Yeah, that's right. Schedule. Okay. To be changed needs be. First of all, introduction. Today, limits and continuity. Second, derivatives. Differentiability. Differentiability. And differentiability. More on that. And local extrema. Global extrema or extrema under constraints. 5 double integrals or more than double integrals. And 6, what's next lecture? Changing the variables or substitution if you want. Substitution in a multi-variable integral. Now, what write it down? Additionally, want to talk about here? Where is it? Not easy, but let's see. Where is it? Taylor series. In addition, hopefully we'll make it. And I don't think so. I have to think with myself where actually to put it. Taylor and chain rule. That's what we want to discuss here about multivariable calculus. Okay, so let's begin. Introduction. The basic concept is very simple. We want to discuss functions from r to the power of n, more generally speaking, some subset of it, to r. We discuss functions functions such as f from r and r, and more precisely, functions from some a to r, where a is a subset of Rn. I mean, know it from, if you want, from psi school. The function 1 above x is not defined for every x in R. It's a function from a subset of R without 0 in this case, to R. So generally speaking, we talk about functions from subsets of Rn to R. One can talk about functions from Rn to some Rm, but we will not do it in our course. The generalization is not so different from what we are going to do here. A basic concept I want to use from time to time is acknowledging what do we actually know about the single variable function when it comes to limits, to derivatives, etc., etc. And then what is similar, what is different between that and the functions of more than one variable. But before that, talking about the introductions, I decided with for n equals 2, we need a 3D vision in order to paint or grasp the graphs of such functions, in order to draw whatever graphs of such functions. You are not expected. We are not expected do it by ourselves. But in order to, explain something, we can use 3D graph creator or something like that. For example, we can look at the following function. Fxy is x squared plus y squared. It is the generalization of a parabola to a two-dimensional or three-dimensional, depends on how you can look at it. Space, it's called a paraboloid. Okay, the graph is a paraboloid. And let's do it together. Share my screen with you, the browser as well. We can use Wolfram for such simple tasks, but today with Jeppet and whatever, let's use Jeppet. Let's see how he does. How about you? Okay. Jeppet מה שלומך? תבוא בבקשה למצב absolute. Told you about the absolute mode of GPT? Absolute mode? Yeah, because without all the, oh, how are you? Yeah, smileys. בבקשה, גרף של xy שווה x בריבוע פלוס y בריבוע. יופי. But then again, for simple tasks like that, you can use Wolfram or not have to use the AI for that. Analyzing, yeah, no, why are you talking so much? No, you give me the. That's Wolfram. Rudolph Wolfram. 3D flat, x squared plus y squared. And here is it. Looking from, above. Of course, it cut itself as some square around it, some cube around it. It's an infinite graph unless you take a specific domain. And this is the contour plot. It's called in Hebrew Kaveh Gova. I don't know how you say it. Eh?
Hyper.
I don't know, but when you look at the map, usually the map is two-dimensional map. How can it show you the mountains and the valleys, the 3D aspects of our reality? Use some lines, and across the lines it writes the height, probably according to sea level, but it depends on what map you look at. So let's take it from here. I mean, I can without even downloading it, just Wiki Shift S it. Yeah. But for n greater than 2, we need more than 3 dimensions to imagine the graph. Which is what? No, no, yes, I need to get back to the yeah. So again, for n greater than 3, we need more than 3 dimensions to imagine the graph, which is pretty difficult. To the human mind. One can use some animation, probably grasp the fourth dimension. I'll show you. Let's get back to the browser. If I look at probably tesseract, it's a simple one. It's like a 4-dimensional cube. And as far as I remember, in the Wikipedia page, it has some like here, see some like kind of animation trying to grasp the concept of the fourth dimension, which is I don't know if it's easy to tell. I mean, every facet of this cube is actually a cube itself, a 3D cube. Like when it comes to a 3D original cube, every facet is a 2D cube, which is a square. So in single variable calculus, the graphs, the geometry was mainly wasn't usually a part of the formal proofs we've written down, but it was actually very helpful understanding intuitively stuff, and the integral is the area between two functions, etc., etc. And here, when it comes to n equals 2, we can still talk about the geometric part and imagine it in our little narrow minds. But when n is greater than 3, it's basically, as I mentioned, it's difficult. It's basically impossible. We can't think of more than 2 dimensions. Okay, so this is the functions we want to discuss. And as I said, want to go to do a quick run in this following subject. And our first subject is the subject of limits. Now, as I mentioned, I don't want to get into the formal definitions with epsilon and stuff. And I mean, one can write it down, and maybe you know what? Maybe I'll will write it down, but you don't have to actually use it or something like that. The basic question is simple. Where does the value of fx goes when x goes to sub a, where x and a are vectors in Rn. For example, what is the limit of, let's say, x and y goes to 0, 0 of the function x multiplied by y, x squared plus y squared? Does it exist? Does it not? Here the x is actually xy, because it's a vector, and the a is 0, 0. Formally, in order to define the concept of limit, we first need to have a concept of distance. Yeah, x is getting closer to a, the value of f is getting closer to some value, whatever, but f, the value of f is a value in R, because our functions are from Rn to R. But a and x are vectors in Rn. How do we define distance between two vectors in Rn? Now we know how to do it from linear algebra 2. How fascinately everything connects. Indeed, we already know how to define the distance between, let's say, x and a Rn. Is the norm of the difference between x and a. So formally, I want to write it down in different color because it's not very important to me when I talk about the technical part about the tachlis, and then I'll show it shortly. But let's start to just call this time. Let's do. So the formal definition should be something like that. Let f be some function from Rn or some a to R. Let a be an Rn. The limit, this goes to a of fx, is some L if for every R is used to define the limit of function using sequences or using epsilon and delta? Both. And what was preferable, the sequences or epsilon delta? Epsilon delta, so write down epsilon delta if for every epsilon greater than 0, there is some delta greater than 0, that's לאו טובים for every epsilon. If the distance between x and a is smaller than delta, then the distance between fx and L is smaller than epsilon, and yet again, between f and its limit, I can write down just the absolute value because f is a number in R, but the x and a are vectors in Rn. And one can use the sequence, the Heine formula, the Heine phrasing, and using sequences. No, it's not very important. Yep, that is right answer. The sequences, the limit of x to x is L.
Normal for for functions, so right?
Yes,
Yeah, so you're not it's not inside of the multivariable part, right?
I am. The only difference visually is the norm here instead of absolute value. Because x and a are now some vectors in Rn and there's numbers in R. Well,
Did I go into the linear algebra course by mistake?
it's all coming together.
We're going from a vector to a real number.
Yeah. For example, here we have some vector xy, and then it becomes a real number.
Alright.
I mean, we can discuss functions from Rn to Rm. Vector becomes another vector, but we are not going to do it.
What's the way of saying that we have two inputs? So
Yeah, more than one input. It's a nice way to put it. You know what? Let's give up for now, at least, about the phrasing using sequences. But what do we actually do? Actually, tachlis, I would say in Hebrew. So actually, Hebrew, whatever. Actually, no, what actually? We know in one variable the limit exists if and only if the one-sided limits exist and are the same. They're equal. Now, I want to put it in other words. We, for first look, it will look, you know, overdoing the exaggerated, but I want to generalize it to more variable, and then it will make sense. We can, you know, we can draw it if we want. It's because it's very simple. One can say something like that, you know. You have the point A here. No, you want something. I want to wait. Okay. There's some point A here, and we want to if we want the limit to exist, we need that no matter where do we from where we are going to A, we will get the same. What is the should be sticker. Okay, like that. No matter from wherever you are getting closer to A, the value of F should be getting closer to L. Now, when it comes to one variable, where our domain is just a line, the real line, every way, every path, that's the word, every path to the point gives us the same limit. The word every is a big word for two path, one from left, one from right. Yeah. But I want to use this phrasing to generalize the tachlis concept of limit to more than one variable. We can
more than one.
yes, two variables should be a plane. More that we cannot imagine. We can say it in the following way. for every path to the point A, we get the same limit for fx. Intuitively, there are two paths here, one from the left, one from the right, but it's still every path. The word every student here will get, there's just two students, but technically speaking, it is true. For every way, every path to the point A, the function f has the same limit. Now, what can we say about more than one variable? We can say the same for or about functions. No more than one variable, more than 2A, right? One variable. The limit of f when x goes to A is L. We'll write it down, something like this. If only if f for every path to the point A, the limit of f is L. Or on every path point, maybe it should be on every, it was just a little add something going on the path. So for on every path point A, the limit of f is L. Now, as we mentioned, you look, let's say, the two-dimensional case. And most of our examples will be in the two-dimensional. We will mention from time to time 3D, I mean X, Y, and Z as inputs, examples, and maybe one or two, not just today, for all the 6 lectures coming up, some n-dimensional, general n-dimensional problem. Now, let's say the point is the origin. It's the most common example here. How many ways, how many paths can we walk to the point 0, 0 here when our domain is the plane and not just the real line? 4, it's the intuitively correct answer, but it's slightly more than 4. There are infinite, yeah, because we're not bounded to the axis. Now it's not just the x axis and the y axis are our domain, but all the plane, all R2 is our domain. So we can come from here and from here and on some parabola and going through the function of sinus x, just getting jiggy with it, etc., etc. So the phrasing is the same, but here we have if n is greater than 1, 2, and so on. We have an infinite number of paths going to the point A. So intuitively, it is easier to show that the limit of x to L does not exist from all this infinite number of paths. We need to find two different paths with different limits. On the other hand, it should be harder, tougher, more difficult to prove that the limit does exist, because I need to consider infinite number of paths to the point and not just two, the left-sided and right-sided. So, what I want to discuss here, as I mentioned very technically, is how do we show that the limit does not exist? Because it's easier, let's begin with it. Do some 3 or 4 examples, give you intuitions. How do I know before I start the exercise that the limit shouldn't be existing? And then we will discuss how can we show that the limit does exist. We will first discuss how to show that the limit does exist.
Someone needs to number of I think then the rule for like one event on the red.
No, maybe each one of them can be different from the others. As long as you have two with different limits, you're good. Or you're better. You're good, you know the answer. That's good. And then we'll explain how to show that the limit does exist. It would be exists here or exist? Grammar. I don't know. No, maybe that does do the S job there. Okay, so we focus. I'm not saying that every example will be that way, but it's the common type of examples. Many of them here in Nir's practice, homework, and in the final exams will be of that kind. We are focused mainly on limits where x goes to 0. If x goes to some a, we just substitute instead of x minus a, and it goes to 0. We will use the following method, which actually works for every point, but again, we're focused mainly on limits where x goes to 0. First of all, we check the axis. That's why we write it in plural as well, or should be something else. Y is 0 and x is 0. How do you actually check it? What does it mean to calculate the limit over on some path? We will see it in our first example and all the examples to come. If they are not enough, because you get the same limit, we check straight lines, something like y equals k multiplied by x. Because we're going to 0, so y multiplied by k multiplied by x is actually going to the point 0, 0. And then if needed, some parabolas, mx, and so on. Of course, and after I do my examples, I can show you it. One is the lecture here, can generate an example where only every path y is 0, y is x, y is x squared, y is x third gives you the same limit, and only y equals x to the power of 2026 gives you a different limit. And show you how to do it, but talking about the tachlis method to do it, that's how we roll. How do we finding a limit doesn't exist? And from the beginning, how do we actually know, intuitively speaking, that the limit does or does not exist, how do we know that the limit should or shouldn't? Should not exist. Oh no, it's no, it's not. Well, it's intuitively in bold, okay? Intuitively, if the degree of the numerator is greater than the degree of the denominator, then the limit exists and it is 0. Otherwise, the limit does not exist. Okay. Let's go through some examples. Now, examples was the limits that does not exist. Okay, let's begin with simple one. Limit of xy goes to 0, 0, x squared minus y squared above x squared plus y squared. Now, intuitively, what is the degree of the polynomial in the numerator? 2, yeah? Agree. And what about the denominator? 2 as well. So 2 is not greater than 2. The limit shouldn't exist. Let's write down formally. On the path x equals 0, y equals 0, which is the x-axis, we get here y is already 0, x is the one left to march to 0. So we are having going to 0. No, yes, y is 0. X squared above x squared. And what's the limit of that? 1.
Don't care about the phone.
But what? What?
Quadratic linear, but you haven't used.
Because I'm talking about paths going through the origin. So straight line going through origin, the constant is 0. Yet again about parabolas going through the origin.
But you said 1 to 0 in this specific case because the linear testing is 0, 0, right?
Yes, 0 here is the origin, is the vector 0. With 2 variables is the point 0, 0, 3 variables 0, 0, 0, etc.
Yeah, what I mean is you will put something different depending on what point you're testing, like what the convergence point. Like
Yes, but as mentioned, in most cases, the common exercise is 0.
Okay.
And let's say it's the point 1, 2, 3, 4. One can substitute x minus 1, 2, 3, 4 and get the limit goes to 0. That's a big problem here. On the other hand, what do we get on the y-axis when x is 0, y is left to go there on his own or alone? No, what are you doing? Minus y squared above y squared, which is minus 1. So different limits on different paths, the limit does not exist. One can plot this case using Wolfram or something. No, let's ask him. Wolfram, why don't you plot us x squared plus y squared above s squared minus y squared? You can see that at 0, some shenanigans happen. See the graph. Some origami, yes, Yamete Kudasai. Yeah, when you're going to the point 0 here in the center from different directions, you will get different values of the function f. Yeah, very nice. You want me to paste it in the leaks? No, you don't have to. Not so important or necessary. Okay, different limits, the limit does not exist. Now, let's give you another example where the axes are not enough. We need to use some different type of path to the point. That's x multiplied by y above x squared plus y squared. I mean, first of all, we can use the y equals 0, totally fine. But when y equals 0, we get x multiplied by 0, which is 0, and the denominator goes to 0, but the numerator is already there, so the limit is 0. Now, for my next trick, I will use a different color. Control V. Let's make it blue. Our secondary color. Okay. On the path x going to 0, we get 0 multiplied by y, 0 squared plus y squared, which is 0 above y squared, and yet again, y squared goes to 0, but 0 is already there, so it is just 0. And here we got the same. Not much helpful. Assuming helpful is with one L at the end. So mentioned when the x's are not enough, we can use straight lines y equals x k multiplied by x. If they are not enough, we can use y x squared, whatever. Let's do it on the path y equals x. What do we get? Notice that the path actually goes through the origin. The path y equals x plus 1, for example, is not. This is not good. It is x squared above 2x squared, which is and it is not 0. And I can copy my final words from the previous example. Different limits and different paths. The limit does not exist without the s, right? I know that. Notice should have done it before we started the example. Yeah, intuitively speaking, one can formally define it. It's not necessary. Intuitively speaking, the degree of the denominator is actually 2. What is the degree of the numerator? Intuitively, what comes to your first comes to your mind?
If it's someone do now.
Yes, I mean it's not formally speaking, the answer is not actually yes or no, but intuitively speaking, yes. You multiply something of degree 1 with something of degree 1, the outcome is of degree 2. So yet again, the degree of the numerator is not greater than the degree of the denominator, meaning that the limit shouldn't exist, intuitively speaking. Let's do a different example, and then we can notice something and move to the how do we do have a limit. Let's begin with x squared, x third. I think it's good enough. How many rude boy is good enough? I think it is. Now let's go with x. X. I think we are good enough. Are we? Okay. Here, intuitively speaking, the degree of the numerator is 4. Should today multiplying something of degree 3 with something of degree 1. What is the degree of the denominator? Should it be 6 or 2? The mean between them? Well, going with 6 means that the degree of the numerator is not greater, which means that the limit shouldn't exist. But if we try and fail, we can move to the second part. How do we show that the limit does exist? But now, as an example of something good student, will probably get the right answer. We still can use the first axis. It's totally fine. Will give us the correct answer. It is x third multiplied by 0, x to the power of 6, 0, which is 0. Now, we can just copy and paste it, so it's not very hard, but we can see that just in the example B, here giving x is 0 will not change much. Let's see if we paste it in blue. Yeah, good point. Still 0, not very helpful.
Y equals x cubed.
We can, and it will work. But let's do it quickly. Let's run through the not so helpful cases. On the path, that's B. Leave it B. Ah, there's something else. Wait, he's just silent, isn't he? He was worried about you.
I mean, just putting at the on the table, I think putting at the bottom of the decided.
If we walk on the path of the part of this type y equals k multiplied by x, we get the same result. I mean, is x third multiplied by xk, kx, x, kx. Now we can use x squared as a common ground for the denominator, which gives us this. And then x squared leaves us with x squared in the numerator, which is still 0 because the numerator goes to 0 while the denominator is not zeroing. And one can check the path y equals kx squared plus mk will lead to the same result. As mentioned here, we do have hope going on the path y equals x third. Then finding the stars arranged in the way we need. And finally, the limit we get is non-zero, but it is not. Here we are. Let's copy our different limits, a different path. The limit does not exist.
What I'm not understanding here is this is all for the limit from the origin.
Yes. But yet again, limit goes to a different point by a simple substitution. Yes.
Yes. So what I'm not understanding is why can't you just set y to be x cubed? Is it just because it's another valid path that can exist?
Yes, when you're fitting number of paths, one of them is the graph y equals x cubed, and I'm going on this path to the origin. Ask yourself, what is the value, or where does the value of f goes?
Probably you show us the graph and understand a bit better, but yeah.
Yeah, but yeah, yet again, we've already looked at the graph, which was pretty difficult to understand.
Yes, okay.
Yes, well, we can look at it, but here the function was x x third multiplied by y above x 6. Yes. So here again, 0 is something here in the valley. I don't know what to enlarge it. I can enlarge it, moving it from different type of view. Wolfram is too primitive to do so. We're looking for some other 3D graph, but we may Desmos, maybe Desmos, I don't know. I don't know how to use Desmos actually, but fxy is x third multiplied by y. No, also yes. Above x to the power of 6.
You need to, I mean,
What?
I was saying you can select everything to do division, but
Yes,
it
yes.
doesn't matter.
So how do I, what is it? Yes, you look at from above, you get some nice, yes.
Like,
Yes, if you zoom in and zoom in and zoom in, you get some nice thorns here, whatever it is, around 0. But the limit does not exist. So, and you can see here where my cursor goes is the cube. Why is the cube? It causes the problems. Yeah. Good for Desmos. Any questions about the graph here? Yeah, again, I'm not expecting myself to know how to draw such stuff, yes, but using some 3D grapher, we can, at least when it comes to two variables, imagine how it should be. Okay. Now, technically speaking, generally, then move on to how we show regularizability. Generally, the limit, let's do something else. x to the power of n, x to the power of 2n does not exist. The path y equals 0 gives 0, and the path y is x to the power of n gives half. Moreover, every path y equals xn for m smaller than n gives 0 as well. So here's an example. For example, for the test, okay, the limit of x to the power of 2026 above 5052. Oh, how do we disprove it? Need to use the specific y equals x power 2026 path. I'm not going to write it down, but one can think of an example in which every polynomial path gives us the same limit 0. But you need to use some exponential path, for example, y equals e to the power of -1 above x squared or something. Yeah. Not now, not today, what to say to the god of exponential, but one can think of a limit in which every polynomial that goes to 0, when x goes to 0, will give you 0 as the limit. But this exceptional exponential will give you something worse. Different paths with different limits, meaning that the limit itself does not exist. But not today, not now. Any questions about that? Okay. So, how do we show that the limit exists? First of all, important, the concept of continuity is the same as f is continuous at some point A, if and only if. It is if and only if, but it's not a mathematical, logical statement. It is a definition. So, all right, it's just if the limit where x goes to a of fx is just fa. Moreover, just like single variable calculus, the elementary function are continuous at every point they are defined at. Just like in my variable. As I said before, you should, in your head, compare between the one variable function and the functions and the multi-variable functions. What is similar, what is different. It's easier to understand that way. without so. For example, let's say I want to, no, let's go for the 4 variables, whatever, x, y, z, w. And the function is x plus 2y plus z plus 1 above w squared plus sinus x plus x, y, z, w plus 2 to the power of w plus 6. Impressive, but the denominator is not zeroing at our point 0, 0, 0, 0, so we can just put it in and get our value, which is, as far as I can see, 1 above 7. Zero, 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 zero. Okay, not very impressive, but do the job. Secondly, if we can, or if we can, if substituting, so write it down. Substituting some an expression of x, y, z, and so on with t gives us one variable limit. We can calculate this limit with every method we want from the first verse, using every method we want. For example, say I want to calculate the limit of x, y, z goes to 0, 0, 0 of e to the power of minus x squared plus y squared plus z squared above x squared plus y squared plus z squared. For example, now, then write it down as 1 above blah, 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 multiplied by 1 above blah, blah, blah. I mean, using some of the power rules, we have some negative expression in the power. You can put it in the denominator. And here, well, of course, the limit. If we substitute t to be 1 above blah, 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 when x, y, z goes to 0, 0, 0, we have p goes to infinity, right? Because the denominator goes to 0. And then, oh, so our limit becomes the limit of t goes to infinity, t multiplied by 1 above e to the power of t, which can be written as t above et. Now, one can use L'Hopital. One time it's enough. One can say, you know what, we know that polynomial is eaten alive by the exponential, so the limit is 0. Okay. But of course, most of the time, these are not the cases. We cannot simply put our values because the denominator is zeroing or something. And we cannot substitute t for some expression of xy to get one variable limit. What can we do? What can men do against the reckless limits? It comes to the limit that intuitively exists. We know that the degree of the numerator is greater than the degree of the denominator. How do we prove it? So, besides, now something, our main tool is sandwich. We look at the absolute value of our function, which is always greater than 0. By sandwich, it is enough to find a greater expression that goes to 0. How do we do it? We use, in order to get to 1, we use, I don't know, the triangle inequality and the small denominator big fraction logic. Okay, it's very a general description, I like to call it. Let's do some examples. One, two, three, let's write it down. Let's begin with x and y goes to 0, 0. X cubed plus y cubed above x squared plus y squared. Got the cold. I give the cold. There's some Family Guy sketch. You know Family Guy? So the doctor is called Dr. Hartman or something like that. So Quagmire is Dr. Hartman is mentioned, and Quagmire goes like, "Oh, I hate Dr. Hartman." He says one time he says, "I got gonorrhea." I don't get gonorrhea. I give it. Something like that. No, I don't get a cold. I give the cold. May Allah be praised. Here, intuitively speaking, the degree of the numerator is 3, and the degree of the denominator is 2, and 3 is actually greater than 2. Our first example of a limit that exists. So we know that the limit should be 0, but how do we show it? We look, first of all, as I mentioned, at the absolute value of the function, which gives us the one of the sandwich sided by 3. And we need to find the bigger expression that goes to 0. We know that when the numerator and denominator cancel each other, the expressions we are left with are easier to explain, or easy, not easy, easy. It's easy to explain why they go to 0. So we can do following algebraic fun. First of all, we have summation. In the numerator, we can write as different fractions. Now, we know it is smaller than. We don't actually need to use here the triangle inequality, but no, we need to do it. So now, every fraction has its own absolute value. We can use the small denominator, big fraction logic. Here we can give up on y squared, and here on x squared. It's not a random choice. We do that, and now the x's cancel each other, and the y's as well. And without a denominator, we know that the expression, this function xy does go to 0, because as I mentioned before, all our functions are continuous, just like an operable. In other words, if you can put x and y equals 0, you just put it. Yeah.
Why wouldn't be bigger than 0?
Because it's an absolute value. Yeah. So by sandwich, proofing by lunch, the absolute value goes to 0. And so we know from our first course, something with absolute value goes to 0. It goes to 0 without it.
Why can't you just take out y squared and x squared from the last part?
I can do reality about it can be whatever I want. No, but I have a goal, right? And they are not beyond your understanding. We need to achieve some expression that it is easy to say about it, yeah, it goes to 0. So we need to cancel the numerator and denominator. We can give up on whatever we want here, and the expression becomes bigger because we look at a smaller denominator. But
So it's what the becomes square.
yes, exactly. If it was x third was problematic. But as usual, the exercises are solvable. Any other questions? Let's look at a similar example, and then a similar but something different. Let's say we have x squared multiplied by y, x cubed multiplied by y cubed. Here it would be even easier. I mean, we don't need to write it down as two different fractions. One could say, you know what, we can just give up about the y in the denominator. We could give up on the x as well. No, why I didn't copy it correctly. Multiplication now. We're left with x, y third, which goes to 0. And by sandwich, I mean, I'm just copying and pasting, so why not? Why shouldn't I? By sandwich, this nice little fella goes to 0. So it goes to 0 without the absolute value as well. Now, this is a very simple example, very similar to the first one. I want to use this example to show you a different example, similar to this one, but with the slightly different numbers. Let's say 4 instead of 2. here, we cannot do this simple trick. Let's write it down and then delete it. Erase it. X to the power of 4 and y to the power of 4, we are left with x to the power of 4, and it's not good. We still have a denominator. But on the other hand, intuitively speaking, the degree of the numerator is 6, multiplication of degree 3 and degree 3, and the degree of the denominator is 4. 6 is greater than 4. The limit should be 0 by our intuition. So, how can we overcome the obstacle? If it was x plus x6 plus y6, we could do it. Yeah. So here is for what's actually called the means inequality. I don't know exactly how I was told it in the Infi1, but the geometric mean is always smaller than the arithmetic one. It's called mean inequality in English. What?
Arithmetic mean, geometric mean.
Yeah, but how do I, what's the name of the Wikipedia page?
Yeah, plus PM plus H.
Oh my God, you're right. It's horrible.
Arithmetic mean H.
Harmonic one.
We looked at it, we need this one.
Yeah, you don't, but okay, let's give up. How can we, yeah, in order to, give up on understanding the Wikipedia page. In order to not want our limit or our gazim in the heights. In order to advance, I don't want to say it, march forward. Yes. We can use the following inequality. If you have multiplication of a and b, it is always smaller than a squared plus b squared. One can easily show it. No, multiply by half. Who is it? Multiply by half. But we don't need the half. We know that a minus b squared is greater than 0, which is which yields to right arrow. Oh my God. Long right arrow. A squared minus 2ab plus b squared, which gives us that 2ab is always smaller than a squared plus b squared. And of course, it will be multiplied by divided by 2. It still be even smaller. And now let's write it with the half. It's enough. That. And so, in our example, 0 is smaller than absolute value of x third, blah, 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 which is smaller because we are looking at the greater numerator, x third squared plus y cubed squared above 2. Well, first of all, the 2 can go outside, go for a walk. And secondly, it is x6 plus y6 above x4 plus y4. And here we can use the same method we used in the first example. First of all, writing down the fraction as the sum of two fractions, one for every expression in the numerator. Secondly, triangle inequality. Every word give own absolute value. Here, the good old small denominator greater fraction. We do it using our brain. We're left with half of y squared plus x squared, which goes to 0 without any expectation. And this is the y sandwich, blah, blah, blah. There is no unused. Goes to 0 even without the absolute value. Any questions about that? Okay. Something last thing today. I call it polar coordinates. You maybe you're already familiar with the concept of substituting x is r cosinus theta and y is sinus theta. R sinus theta, of course, yields, why not? X squared plus y squared is r squared. So x and y goes to 0. If and only if r goes to 0. So in order to calculate limits in which x, y goes to 0, 0, one can substitute and check if the limit is the same for every theta. I'm not very fond of this method because when the examples are a bit complicated, it's sometimes not so easy, not so clear to understand if the limit depends on theta or not. But let's look at this simple example. If we change the coordinates, where r goes to 0, we have r third cosinus theta cubed multiplied by r cubed sinus theta cubed. X squared plus y squared is r squared. And we are left with the limit of r to the power of 4 multiplied by cosinus third theta sinus third theta, which is 0, no matter what theta is. But sometimes theta appears in the denominator as well, and it is, as I mentioned, a bit tricky sometimes. So we're using our last 3 minutes of the lecture. I mentioned this polar coordinate method. You know, the last week we talk about integrals, we will use polar coordinates in the changing variables in integrals. And if Nir wants to show you some examples using polar coordinates, calculate limits, he's welcome. And you can use it if you want, calculating limits in the homework, a test, a final exam, whatever. Okay, we are finished. Any questions about today's lecture? Okay, you do you. Meet you on Tuesday. Talk about derivative of such functions, which is more interesting. I don't know. Some things need to be said there. Okay.